I'm going to begin with the applications of deep learning that we saw at Booking.com, some of them. And then I'm going to talk about the life cycle of a model from a data scientist point of view. What are the different phases of a model? And then I'm going to talk about the deep learning pipeline, the production pipeline, which we built using containers. So get excited. Let's start. First of all, yes, who I am. Who am I? I'm a backend developer working at Booking.com as in the deep learning infrastructure team. That's why I'm talking about this thing here. I'm also a machine learning enthusiast, which means I spend almost all of my free time, free geeky time, on learning about machine learning and different techniques coming up. And I'm a big open source fan. I have contributed to a bunch of projects like Git that most of you probably use in your day-to-day life. I've submitted a bunch of patches. I'm also contributing the Pandas library, which is a Python library for data analysis. Kinto project, which is a storage engine by Mozilla, and Go GitHub, which is a Go project by Google, and a bunch of other projects. And I'm a tech speaker. That's why I'm here on this stage today in front of all of you. Generally, I talk about topics varying from data analysis, deep learning, A/B testing, containers, Kubernetes. So yes, that's all about me. Let's begin with the applications of deep learning at Booking.com. But before that, I would like to talk about the scale, because I mentioned at large scale what that scale means. So we have over 1.2 million room nights booked every 24 hours across more than 1.3 million properties in more than 220 countries. Let me make one thing clear, that I'm not here to show off the numbers. The point I'm making here is that at this large scale, we have access to a huge amount of data that we can then utilize to improve the customer experience. So let's see how we do that. The first application of deep learning that we saw was image tagging. And when we look at image, for example, this one, the question that arrives is, what do we see in this image? Now, this question is really easy one, as well as a really difficult. So if you ask this question to a person, to someone from this audience, it's going to be easy to say what's there in the image. It's easy to say what are the objects that are there in the image. But it's not an easy problem when you ask a machine to tell what is there in this image. And what makes this problem even harder is that the context matters. What you see in this image may not be what I want to see or I want the machine to detect. For example, if we pass this image through some of the publicly available image neural networks, ImageNet or DenseNet, these are the results that we get. We get information like there is ocean view, there is nature, there is a building. OK, that's good to know. There's a building. But what do we do with it? These are not the things that we are concerned about at Booking. However, these are the things that we are concerned about. Is there a sea view from this particular room? Is there a balcony? Is there a bed? Is there a chair? Or things like that. Now, before you start thinking like, OK, it's an easy problem. You just need to detect a bunch of objects that you have. No. First challenge is that it's not an image classification problem. It's an image tagging problem. That means every image is going to have or might have multiple tags. So it's not just like you classify it as something sea view or balcony. Every object is going to have multiple tags. And to top that, there is going to be a hierarchy of the tags. For example, if you see an image has a bed in it, we are almost sure that the image is going to be of inside view of the room, unless you're in such a room where there is no bed. There is no room. So once we know what's there in an image, we can use this information to help the customer decide what they want. We can help them in deciding what kind of property, what kind of hotel or apartment they want to book if we have this information about all the images that we have for a particular hotel. Let's talk about another problem. So this is a classic recommendation problem where we have a user X. They booked the hotel Y. Now we have a new user Z. There is a debate if it's a Z or Z, but I'm going to stay with Z. So there is a user Z. We want to predict what hotel they are going to like. So we basically want to recommend a hotel that they are going to like. So the objective we have is we want to find a probability of a particular user Z booking a particular hotel. And we have certain features like country or language of the user, where they are coming from. We have contextual features like when they are looking for it, what's the day, what's the season. And then we have some information about the hotel, the item features, like what's the price, what's the location, is it near the beach, does it have a pool or swimming pool or something like that. So I'm not going to go into details of this problem because I'm here to talk about the infrastructure part, and I'm not going to disappoint you. So research has shown that we can get better results for such a problem of a recommendation system if we use deep neural networks instead of linear or collaborative filtering. So once we figured out that there are going to be some certain applications of deep learning which may be really interesting for us as a business, we started exploring this field. And thanks to my colleagues, Stas and Imra, who are probably enjoying the rainy season back in Amsterdam, they started exploration of deep learning at Booking. And now, these days, we have some very cool deep learning models in production. So let's start talking about the life cycle of a model. What are the different phases? So there are 3 phases: code, train, and deploy. In first phase, data scientists write their model, write the code for their model, try out different features, different kind of embeddings, different kind of interactions of different features, and different architectures. And once they know they are happy with the performance of the model, now they want to train their model on the production data. Once they are done with the training on production data, they want to deploy it so that it can be used by multiple clients. So we use TensorFlow, which is a nice machine learning framework by Google. We use its high-level Python API to write our models, because it really sort of standardizes the process of writing the model and helps get the prototypes quickly. Now, these 2 parts, the last 2 parts, train on production data and deploy. These are the 2 parts that constitute our production pipeline, deep learning production pipeline that I've been talking about since the beginning of this talk. So you may argue why training of a model is a part of our production pipeline. That's a very valid question. You can also train your models on a laptop, right? But if you try to train your models on your laptop, you may end up looking like this. Not really happy, right? So there are a couple of reasons. One is that sometimes your training data is so large that you can't really hold all of it in your memory on your laptop. And other more general reason is that your laptops are going to have limited resources, like CPU cores, GPUs. In most of the cases, they're not going to have a lot of powerful GPUs to speed up the training. So if you want to speed up the training, you should not train on your laptop. And we'll see how we do that in production. So we have our big servers, which have a lot of cores, CPU cores, and a powerful GPU support. And what we do is we wrap our training script. We run them on our big servers. Problem solved, right? Not quite. So once we do this, there is a limitation with that. There are going to be multiple data scientists who are going to run their training at the same time, possibly on the same servers. So we might not be able to provide the independent environment that they might like to have. Plus, if they want to use different version of TensorFlow, for example, we need to create some sort of independent environment for that particular training so that it defines what it wants to use, so that we don't really need to have global level dependencies or particular packages. So this is what we do. We wrap our training script in a container. So this yellow thing is, let's consider that as a container. That's the best I could draw, not a designer. So we wrap our training script in a container, and then we run that container on our servers. So now, what is a container? Container is a lightweight package of the software that contains all the dependencies that it needs to run. And then we run that on our servers. Easy. So what that enables us to package all the versions, all the particular versions that we want for our training, package that up, and ship it as a container. So that solves the problem of having multiple different versions of multiple dependencies. And these containers can also utilize the GPU support that we might have on our servers. You can just utilize whatever GPUs we have. So in a nutshell, this is how it looks like. We have our production data in Hadoop storage that we want to use to train our model. We spawn up a new container every time we want to run a training. That container, again, has all the dependencies it needs, has a training script, and it takes the data from Hadoop storage. Once it has the data, it runs the training. And now, while the model is being trained, we want to make sure that we can somehow save that model. We should be able to save the trained model so that we can utilize that later. We can deploy it somewhere. So we save the model checkpoints back to Hadoop storage. Model checkpoints are like the model weights that are going to be that are required to be able to load the model again at the deployment stage. Once we save the model checkpoints, the container dies. Yes, who can be more selfless than a container? It takes birth to do the work that you assign, and then it dies. That's the entire life of a container. So once we have trained our model on production data, we have already covered one step of going into production. So next step is to use this model, the trained model, and put it in production so that people, not people, but different clients can use it to get the predictions back. So this is what we do. We have a simple Python app, which is a WSGI HTTP server. It takes the model weights that we just stored in the last step from Hadoop storage. It loads the model. No. Yes. That's weird. So it takes the model checkpoints from Hadoop storage. It loads the model in memory, and it's ready to serve predictions. So let me cover it again. So to be able to serve predictions from a model, we need two things. We need model definition, which defines what are the features, what are the interactions, and all that stuff. And then we need to have the model weights that we gathered from the training. Once we combine both of these, we load the model in memory. It's a TensorFlow model in memory, and then we are able to serve the request. And to top this, we have a nice way to abstract all this and provide a nice URL where a client can send a HTTP GET request and get the predictions back. In the end, it's as simple as just sending the GET request and getting the predictions back. So this is what it looks like. We have an app that I just mentioned. We wrap it in a container, once again, because having containers solve the problem of so-called, it runs on my machine, but doesn't run on yours. So it contains all the dependencies, and if it runs on one machine, it's going to run on all the machines that support containers. And so once we wrap the app in the container, any client is able to send a HTTP request, all the input features that are required to get a prediction back, and in the response, it gets the prediction. But again, as I mentioned, things are not quite simple at a large scale. So what we need to have is we need to have multiple servers. Easy solution. We had one app. We were not able to serve all the requests properly, so we have multiple apps. We replicate the same containers that we had, put them behind a load balancer, and the client doesn't know how many apps are actually serving behind. It just knows the IP of the load balancer, and load balancer is responsible for rerouting all the requests. Quite simple. But things are not generally simple at large scale. So instead of 6 servers in this, we need to have quite a lot of servers. As we keep on increasing the number of, when I call servers, it's actually this container. So as we keep on increasing the number of containers we have for a particular application, we need to find a way to manage these properly. Because once you have hundreds of containers running a particular app, particular model, things are going to get sketchy. So we use Kubernetes to surround all of this infrastructure that we have. Kubernetes is a container orchestration platform which helps in scheduling, managing, and scaling containers easily. It provides a really easy way to scale up or scale down the number of containers that we have based on certain principles. And it also provides an easy way to make sure that at any point, we have a specific number of containers running. And if something goes wrong, some of the containers die, Kubernetes is going to make sure that it spawns up new containers to maintain that number that you specified. So that was about putting in production. But once you put things in production, a lot of responsibility comes on you. Now, you want to be able to measure the performance of these models on your production server. You want to be able to answer some of the questions like, how is this model behaving? What are the latency versus throughput of your model? So let's say your model is taking some computation time to give the predictions back. But this is not going to be the time that your client is going to see. There's going to be some request overhead. And so in general, the total prediction time is going to be the sum of your request overhead and the computation time. And if in case you send like more than one instances to predict on in one request, for example, if you have n instances that you want to predict on in one request, it's going to be n times of computation time that your model requires to predict. We can see from here that for some of the simpler models like linear regression, logistic regression, or simple classifiers with lesser number of features, the request overhead is going to be the bottleneck because the computation time is going to be too small compared to the request overhead. So you need to be considerate about what kind of model you have and what's going to be the bottleneck for your particular case. So once you have this information about your model, you want to be able to optimize it. And you can do that for two things. So one is you want to optimize for either latency or throughput. Let's talk about them one by one. So first is if you want to optimize your serving for latency. What's the latency? Latency is the amount of time taken by your server to serve one request. And this is from the client point of view. So how can you optimize for latency? First of all, when do you want to do that? When you have some application where you want to show some information to the user real time, you definitely want to optimize so that you can serve that request, serve the response as soon as possible. The first optimization that you can do is do not predict in real time if you can pre-compute. That may sound silly, but in a lot of cases, it's possible that you already know all the space, feature space that you have. And instead of computing real time, predicting real time, you can predict for all those cases and save the results in a lookup table and just use that lookup table when an actual prediction request comes. The next way is to reduce the request overhead. For simpler models, when you know that the request overhead is the main bottleneck for your serving, for serving those predictions, you can optimize to have lesser request overhead. And how you do that? So one of the things you can do is you can embed your model right into the application that is serving. And that's what we do. We load the model right into the memory of the app so that there's no latency, no request overhead to go from the HTTP request to the model. The model is right there in the memory. Once the request comes, it's going to serve right there. Next thing is predict for one instance. Let's say on a web page you want predictions for 3 different models or 3 different instances. When you want to show the information as soon as possible instead of batching it, you should send 3 requests with 1 each prediction. This is a specific technique for speeding up the prediction. The quantization. What that means is that you change your float 32-bit types to 8-bit fixed type. How is that going to help? Now, your CPU processor is going to hold more amount of 4 times more data in the registers, and it's able to process the data faster. So that means you are going to be able to compute the predictions faster, 4 times faster, to be accurate. And then there are some TensorFlow-specific things, which really depends on what library you use. You use TensorFlow, so there are some techniques like freezing the network, which means there are some TensorFlow variables in the computation graph, and we can change those variables to a constant so that there is less overhead when we try to compute. And the next thing is we optimize for inference, which means we remove all the unwanted nodes from the computation graph so that we don't really compute unnecessary things that we don't need in order to predict something. Now, the second application is optimizing for throughput. Now, what is throughput? Throughput is the amount of work done in 1 unit time. So when do you want to optimize for throughput? Let's say you have some cron job or Uzi workflow or some offline work that needs to be done every night or every hour or every 10 minutes. There you don't really care about when a particular request arrives or when it gets the response. What you care about is how much time it takes to do this bunch of work. So that's when we want to optimize for throughput so that we just care about how much work is being done in a particular time, and we just don't care about when a particular request or how much time a particular prediction takes. Again, the first thing we can do is don't predict in real time. And this is not that I'm trying to enforce this, that you should do this, but this is something that you should always consider. Is it possible to pre-compute and have a lookup table to serve the request? If so, always do that. It's going to be much faster. OK, batch request. So once you know that you're going to do millions of rows of work, it's better that instead of sending 1 request per prediction, you batch your input features. Like you have thousands of input features right in 1 request. And then you send the request at once and get the response back. So by doing this, you reduce the request overhead. Because if you send 10,000, for example, predictions in 1 request, you are going to get rid of all of the request overhead that was going to be there. This is really interesting. Parallelize your request. So when you want to have a lot of work done, instead of waiting for your request to get this response back, you do the work asynchronously. You send the request parallelly using multiple workers and do some sort of callbacking option to make sure that you collect the results better and faster. So let me try to summarize what I talked about. First of all, I talked about the training of models in containers. We spawn up a container every time we want to train, get the data from Hadoop storage. Once the training is done, store back the model weights into the Hadoop storage. Now, the next step is to be able to serve those model weights in production, in containers. We spawn up containers which have the Python app that we want to run. It loads the model definition as well as the model weights. Once we have that model, it's ready to be served corresponding to any HTTP GET request. And next is we optimize our serving for particular applications. It may be real-time application where we want to optimize for latency. It may be some offline application where we want to optimize for throughput. That's all I have. And if you want to get in touch with me, you can get in touch with me on all of these social media networks. I go by Sahil Dua 2305 username. And yeah, thank you.